Okay, recording is starting. So hello everyone who's arrived, and thank you everyone for coming. I'll admit some extra people. So we've got our first talk of the month that's related to ArkLib. We'll have 3 talks this month about ArkLib. And so the first one is by Quang, who is very much, I think, the creator of ArkLib and the person behind much of the work in ArkLib. And so this talk will focus on compositional verification of SNARKs in Lean, and I guess a lot of the underlying framework and theory behind ArkLib, as well as some of the implementation details. Quang is a PhD student at CMU. He's also worked on Jolt and has contributed a lot of research to both kind of normal, regular pen and paper cryptography, and obviously over the last year or so has been doing a lot of work in Lean as well. So it's very exciting work, and it'll be, I think, quite a good talk. If anyone has any questions, you can leave them in the chat and we can get to them at the end. Okay, up to you, Quang.
All right, thanks so much for the introduction. So this is going to be a talk about ArkLib as a whole, and with a focus on the parts that I have contributed the most to. There are many other wonderful parts, for example, about coding theory, about Fry and other protocols that people are working right now in ArkLib. And I hope the next few talks will give some details on those. So it's an open source project. I'm sorry if I did not put the names of anyone in this attending this who contributed, but I did not put the name here, so sorry in advance for that. And yeah, let's begin. So the goal of ArkLib is to have a formal verification framework for SNARKs. And I think we all know what SNARKs are, but let me just refresh your memory for a moment. SNARKs are succinct, non-interactive arguments of knowledge. These are very short and proves that a prover can just send over to a party called the verifier. And in fact, any party can see the proof and verify that whether it is correct or not with respect to some statement X, this is the public statement, and some relation that X is supposed to satisfy, maybe together with the witness W. The proof here is supposed to be very short, and we'll see later on like exactly how short they are in the context of Ethereum. As proofs go, they need to be complete and they need to be sound. And Ethereum is investing a lot in these SNARKs, and in particular in zero-knowledge virtual machines. But also, these proof systems are finding a lot of applications in other contexts as well. So here are some buzzwords and some company logos that are in this ZK space. And let me just highlight 2 main applications of SNARKs that I think people are very interested in. The first one is that the zero-knowledge property of these proof systems allows you to do identity verification in a private manner, meaning that you may have some private information about yourself, such as your digital ID, your financial history, your health data, and so on. You don't want to share these, but you want to prove that these data satisfy some property, or you want to put them into some computation and say that this computation ran correctly on my private data. This kind of application is now being rolled out in a large-scale manner, especially with Google Wallet. And the other kind of applications that people are excited about is through these succinctness features, especially with Ethereum. When you try to scale the blockchains, you need to use ZK SNARKs among other things. So you have a block of transactions that comes, say, every 12 seconds. And you want to quickly generate a proof that this batch of transaction has been correctly executed. And then you post this proof instead of the transactions themselves. And this saves a lot on the bandwidth and also on the verification time. So this is now a major initiative of Ethereum, and basically the reason why ArkLib exists. It's because we want to make sure that these proof systems can be production ready for running on Ethereum itself. And part of what makes them production ready is not just about the performance, although here you can see this is, I just pulled this up today. This is what the performance looks like right now for these proof systems. You can prove an Ethereum block using multiple GPUs in just a few seconds. The potentially bigger question here is that, are these proofs actually sound? Of the proof systems themselves, are they sound or not? And if they're not sound, then the consequences can be catastrophic. In the identity verification example, your ID can be forged by anyone else. And in the context of blockchains, well, now you can prove that you actually own a lot of money. And so this leads to unlimited money printing, which is a big no-no. And somewhat depressingly, the soundness bugs are extremely common in proof systems. And so here are a number of, by no means exhaustive list of mistakes, bugs in proof systems, both from the point of view of like a theoretical exploitation of the back end of a proof system to constraints, bugs in the front end. And when you implement all of this, there will be lots of other implementation bugs that show up. The actual list is probably like 3 times this much, these amounts here. This is just a sample of what can go wrong in the 10 years that ZK SNARKs have been around. So with all of these problems, we need to invest in formal verification. What this means is that we need to formally specify in Ethereum prover these protocols, these proof systems, and then formally prove that they satisfy the desired security that we want. And in fact, this is basically a standard in the kind of classical cryptography that is widely deployed nowadays. So there's a lot of work, a lot of tooling on the sort of key exchange kind of protocol. And this goes all the way to the low-level implementation of these primitives and of these protocols. So we have had, the community as a whole, have built a lot of wonderful tools for formally verifying cryptography. But when it comes to these proof systems, we face a problem. Namely that these are so cutting edge and so different from what came before that we can't really reuse any of these tools. Because of this, we need to build new tools that is tailored and tailored to the applications that we want, which are SNARKs. And along the way, we might as well try to base it on something on a Ethereum prover that is getting a lot of traction, which is lead. Okay. So people have been doing it. People have been building specific tailored formal verification systems for ZK proofs. And the big thing that ArkLib tries to fill in is that it tries to fill in the back-end verification parts of these proof systems. So I'll tell you a bit more about just the precise scope of ArkLib, which admittedly is quite large. So this is what ArkLib is meant to be, to focus entirely on proving the protocol security of SNARKs, with a focus on making it general. So we want to be able to pick any SNARK in the literature or that is being deployed in practice and be able to specify them in this framework. And second of all, we want to be able to prove completeness and soundness or other properties of these proof systems. And we want to do them in a modular manner, in a modular and scalable manner. Because otherwise, we will not succeed in this task at all. It is already hard enough to get pen and paper security proof for these SNARKs, and in some cases, we don't really have a good reference for the pen and paper security proofs. And yet we have to port all of that into a theorem prover, which is lean in our case. So yeah, as I'm talking, if you have any questions, please feel free to ask me. If not, let me keep going to the details of ArkLib. And I guess before that, I want to just give you the general anatomy of a SNARK as they are constructed today, and how ArkLib fits into this picture and tries to provide a framework that can allow us to specify and improve security of all of these SNARK templates. Okay, so a SNARK is just this, abstractly you can think of this is just a single proof sent by a prover to a verifier, or the prover posts on the blockchain this proof, and then multiple verifiers can verify this proof. Okay, if you look more closely at this proof, what happens almost all of the time, except for one exception, which is cross 16, but almost always the proof is constructed as a series of messages. And these messages actually came from an underlying interactive protocol, where the prover and verifier interacts over a number of rounds, and the verifier just sends random challenges and does not have any other randomness. So for these kinds of special interactive public coin proof systems, we have the celebrated fiat-Shamir transform that turns this into a non-interactive proof by just hashing the messages so far to derive the challenges. This is quite standard, and it's one of the goals of ArkLib to be able to formalize this fiat-Shamir transform. So the work on that is ongoing. The next part is that if you look even more closely at this interactive argument, it's actually breaks down into a further primitive, which is an interactive oracle proof. So it's still interactive. The only difference is that the messages that the prover sends to the verifier may now be sent as oracles. So the verifier may not have the full knowledge of the message. It cannot see it in full, but it can only query it according to some specified oracle interface. So an interface here could be the message is a vector of field elements, and then the verifier will ask for what is position 9 in this vector. Can you tell me what field elements is in that position? And so on. So this kind of interactive oracle proof gets compiled into an interactive argument through the BCS transform, short for Ben Sassoon, Chiesa, and Spooner. And the key here is that we want to materialize these oracle messages. And the way we do them is by committing to them, sending the commitments, and then later on, when the verifier wants to query these oracles, the prover will send over the responses along with an opening proof that these responses are correct, according to, like, consistent according to the commitment itself. So these are called functional commitment schemes because the function, you can think of this oracle interface as defining some sort of function on the message and the query. So that's pretty abstract, but it's only abstract because it's been abstracting from a long series of work starting with PCPs, where there's just a single message. This can be very large, and the verifier has oracle access to the message, has sort of vector access to the message. It can query individual positions. Later on in 2016, this got generalized to a multi-round protocols, where each round you can send an oracle that can be accessed via this vector Oracle interface. Okay. So far we just have vectors, but then people realize, well, why not send other kinds of oracles? For instance, what if the message is a polynomial? Then you have a different kind of query that's very natural. You want to evaluate these polynomials at different points, and that gives rise to polynomial IOPs. And then people keep going and say, well, why not just generate this to an arbitrary Oracle interface? And that's what gives us this functional IOP model that ArkLib formalizes in its framework. So with just one representation, we could capture all the different kind of instantiations and special cases that exist in the literature. And in fact, we don't just care about proofs, we care about reductions. And what this means is that if you look at the way that these IOPs are constructed, they are often decomposable into multiple parts. And then each part is like a sort of, I guess reductions is the right word. You go from a one kind of relation on your data to a different data that enforces a different relation. So the game here is that you have originally some very complicated relations that you want to prove, and you incrementally simplify these relations via interactions until finally you have just a trivial relation where the verifier says yes or no. Okay. And in fact, I think that the SNARK literature is also converging to this notion of IORs as the right way to state protocols. So ArkLib is basically following the community's best practices and try to give a framework that is generalizable from the start. Okay, so in terms of IORs, we still want completeness and knowledge soundness. In fact, in ArkLib, we do formalize stronger notions, and we do need to prove the stronger notions such as state restoration, knowledge soundness, and or round-by-round knowledge soundness. So all of this work is underway. And currently, ArkLib does not support proving or even specifying zero knowledge of any form yet, although this is something that I would love a contribution from if you're interested in. But for now, the main focus is on completeness and knowledge soundness and making sure that the ArkLib, the specifications in ArkLib are actually executable. So you can execute it and cross-check it with actual implementations, say, written using Rust or other programming languages. Okay. So the one of the key protocols that ArkLib formalizes, or at least is in the process of formalizing modulo some generic proofs, is that of the subject protocol. So here I just want to provide an example of how ArkLib breaks down a protocol and modularly constructs the security proof. Okay. So the subject protocol is a very classic protocol that dates back to the 90s. And it's a protocol about verifying that the sum of a multivariate polynomial P over some product domain, let's say the Boolean hypercube here, is equal to some target value. So this turns out to be very useful in the context of proof systems because it allows you to basically establish any kind of low-degree relationships between different parts of the data. And the magic of the subject protocol is that using interactions, it can reduce the relation from the sum over an exponential size domain to a single claim about the polynomial at a random evaluation point. And the way the protocol works is that in each round, the prover just sends a univariate polynomial. And oh, thank you. Yeah. And the verifier sends back a challenge, and it does some checks. Some checks in each round, and then it sort of refreshes the protocol for the next round. So this is some check. It's very classical. It's behind many of the fastest SNARKs today. And it has a very clear completeness and soundness guarantees. Right? So for soundness here, basically in each round, the best the prover can do is that it sends some polynomials that may or may not agree with what the polynomial is supposed to be. And if the initial relation is false, then in some of these rounds, the prover would need to send something that will get rejected with high probability. And so if you sum over all of the n rounds, you get this soundness error, the cumulative soundness error, or you can break it down round by round, and you get a round by round knowledge soundness, or just soundness, or sorry, a round by round soundness of D over F. So this is the theorem that we are formalizing in ArkLib, among many other things, of course. So how do we actually go about and formalizing this theorem? Well, ArkLib is centered around the fact that using these reductions, we can compose them in all sorts of ways. And so if we can write down SUMCheck as a series of these smaller reductions composed together, and we can show that these individual reductions satisfy completeness and soundness, then using generic theorems that holds for all sort of composition patterns, we can deduce the security of the overall SUMCheck protocol. So the first thing that we can do with reductions is that we can sequentially compose them together, assuming that they share the intermediate layer. So meaning that what the first reduction outputs becomes the input for the second reduction. Okay. This is basically the original motivation for introducing reductions. And in fact, sequential composition in this way have preserve the security properties that we would like it to preserve. So this is something that is still in progress in ArkLib, that we're trying to prove this generic theorem. But the nice thing is, once we prove this theorem, then it can be used once and for all in all of the SNARKs that we specify inside the framework. Okay. And with SUMCheck, well, I think the pattern of sequential composition is quite clear. You can break it down into each individual rounds of interactions. And what happens is you can define these intermediate relations, and it's also quite nice. You have this very incremental property of the protocol that goes along as you proceed in the reduction. Okay. And in fact, what you can do even further is that you can decompose each of the single round protocol into single message protocol. Like you can specify exactly what happens after the prover sends this first polynomial s1 of x, and then you can specify exactly what happens when the verifier sends back the challenge R1. So you can define all of these intermediate relations, and this basically simplifies the task of proving security. Okay, so that was the first way, and perhaps the most straightforward ways in which these reductions can be composed. However, it turns out that we can't just rely on sequential composition if we want things to be as modular as possible. And so here's the intuition for why we can't really do this. we can't do it because when we do the sequential composition, we need to have this middle thing, this middle statement and witness be the same across the two reductions. And this may not seem like a big problem, but it actually does pose the problems if you want to have reusable components. Say, if I give you the subject protocol that I described like this, how do I use the subject protocols in some larger protocols? And it turns out that you can't really just sequentially compose the subject protocol with other parts of the protocol. Okay, so here's one way to make this precise. Let's take Spartan. This is a sort of a higher level polynomial IOP that uses subject as one of its core components. So the protocol tries to show that the R1CS relation corresponding to the public matrices A, B, and C, along with some public input X and some private witness W, satisfy this kind of quadratic equations. Okay, and the first round of Spartan basically does a single exchange of messages. So prover sends an oracle to the witness, verifier sends back some challenge, and the goal of this is to turn this into a subject claim. So here you can see this is the format of subject. You may not need to understand all of this stuff, but it suffices to see that this is a polynomial, and this is a subject claim. And so we can apply the subject protocol, and at the end of the protocol, recall that the guarantee that we get, or the remaining claim that we have, is that this polynomial, when evaluated at a random point R, is equal to some claim E. Okay, so far this is perfectly intuitive. The only problem is when I put in quotes what I mean by apply subject, this application cannot strictly be a sequential composition. And the problem is quite mundane, but it's also very annoying when you try to formalize this in an interactive theorem prover. And is that the polynomial that subject is applied to can be derived. It's something that is derived from the public statement and the private witness, but it's not quite equal to it, right? And so if subject were to say, here's the input of subject, this P and this T, then the statement and the witness that we have here is not exactly this P and this T. Okay, so that's an annoyance. I think this annoyance basically never comes up when you think about protocols either on pen and paper or in your head, because it's just obvious that this is the way that you're supposed to apply the protocol. Okay, and even for subject itself, you can kind of look at each of these rounds and you say, well, each of this round is actually something that is super simple. You can have a simplified protocol that suffices for each of the rounds, and then you realize that actually each of the rounds is just running this simple protocol, but with a different polynomial Q right here. And well, this is just something that helps in modularly defining subject, but it also speaks to the fact that you can always pull out more structure from the protocol that you think you know very well. Okay, so here is what the sort of problems that we run into when we try to formalize these things in ArkLib. Of course, there are many other problems, but this is one of the problems that I want to talk about in this talk. So the way that we resolve this is through a concept of virtual oracles or virtual polynomials. and this has been described in existing papers. But when you try to formalize this, you need to basically be a little bit more careful and be a little bit more formal. Okay. And so the main thing is that these protocols, like the stamp check protocol, when you apply in the context of Spartan, is a sort of virtual protocol. You have some virtual input, some virtual witness, and then you run the protocol on these virtual data. So we just need to have a good layer for specifying what exactly we are virtualizing. And then we also need to say that when we virtualize things in this way, then it is still complete and sound, and that it doesn't introduce any problems. Okay. So the main setup here is just that we have some inner protocol. So think of this X and W in as the stamp check protocol, and think of the X and W out as the Spartan protocol that we want to apply to. And you basically just need to have a way to turn data from one to the other. So in one direction, we want to map the data to the virtual data. And then when we have the output of running the protocol on the virtual data, you want to integrate it back into the output of the larger protocol. And these two things are basically all that's needed in order to have compatibility between arbitrary protocols. And these two API is also known as a lens in other contexts. So this is kind of, depending on what you think, either very trivial observations or something that is very neat. Okay, so yeah, so with this notion of lenses and virtualization of protocols, we can now, this is just formally, these are the functions that we actually need to define in ArkLib when we want to construct one of these virtualized protocols. So given just these functions, we can now formally describe what it means to lift the reductions, right? Or to virtualize a protocol. So here is from the original data, this X and ABC and so on. We construct this virtual polynomial P and this virtual claim T0, which is 0 in this case. Then we run the protocol. We get some new claim E, which is the last claim of the subject protocol, and then we integrate it back into the public statements. And that's all it is. And then you can work out the same exercise for a single round of sound check in terms of the simpler univariate only protocol. Okay. So so this gives a way for you to properly talk about other protocols in a modular manner. And I think the later talks will, especially about Fry, will lead more into this aspect of both sequential compositions and also these virtualizations. Okay. And then the final wrinkle to figure out is that these mappings, when do they actually preserve the security properties of the proof systems? And for this, I basically refer to what is being formalized in ArkLib right now. Okay. So far in this talk, I basically outlined the main ways that ArkLib was constructed. I did not talk about any particular code snippets that you can go to GitHub yourself and see all the code, but more so about the philosophy and the approach behind structuring ArkLib. So this talk, I basically talk about the most basic building block of ArkLib, which are these interactive oracle reductions, which together with these composition operations can give you full IOPs. But from IOPs, in order to get to SNARKs, we actually need to formalize the commitment schemes and also formalize the Fiat Shamir transformations. and both are active targets that you can contribute to right now in ArkLib. And hopefully we can make very good progress over all of this in the orange box here by the end of this year, so that we actually get an end-to-end formally verified SNARKs or the SNARK verifier for the SNARKs that we care about. So that is one goal that I hope we can achieve this year. Other goals include, well, now we have to connect the SNARKs, which is the backend here that we formally verified using ArkLib, to a bunch of other frameworks that deals more with the front-end aspects. So that means the circuits representations, the circuit specifications, and all the tools needed to show that the circuits are complete and sound. And then finally, we want to say something about the implementation themselves. And so that could mean two things. First, we can rely on existing and ongoing tool for translating Rust into Lean, because Rust is basically the main language in which these SNARKs are written. But another way, which we are also considering, is that we can just write the verifier in Lean already, or we write the verifier in Lean in a way that it can be compiled to some lower level like LLVM or MLIR or some dialects of such, in a way that makes this actually an efficient implementation totally within Lean. So these are two exciting approaches that hopefully will bear fruit also within this year. And then once all that is done, then we can confidently claim that we can have a formally verified verifier for some very complex SNARKs, like zero-knowledge virtual machines for RISC-V. Okay, so that is basically the plan, and is already quite full for ArkLib. Maybe one thing I'll mention in this picture that is missing from this picture is that in order to perform all of these proofs, we need to build up a lot of machinery for actually proving these theorems, and that is the goal of these other libraries that we're building, such as VCVIO and Iris Lean, where we hope to have a good program logic so that we can actually prove some of the very tricky theorems that comes up in this planning right here. Okay, cool. So let me end here with some open questions. I think the first thing I basically have been talking about, which is that actually completing these proofs is a non-trivial task. And here I'm really hoping to have a good framework for this task, and already work is underway by a lot of people on this. The second way is basically do more research on just how to make the SNARK the SNARK literature even more unified and more composable. So one good direction in this is basically these interactive oracle reductions. But I think there are still some more transformations that could be tightened up a lot, could be related to each other, or we could discover some sort of general framework for specifying these compositions. Especially, for instance, when you try to compile an IOP with the commitment schemes. I think there's a lot of disjoint theorems in different papers about slightly different kinds of compositions of this sort, this IOP plus commitment schemes, that it would be nice to formalize them in a very composable manner, and to figure out exactly what it is that that is the core of the argument. Okay, and finally, I think I am very excited about the progress that we're going to make this year, about fully scaling ArkLib to the scale that it needs in order to meet the needs of Ethereum, basically. And that means an end-to-end verifications of some non-trivial proof systems. So along the way, we will, I think, encounter a bunch of further difficulties that might warrant another talk. But for now, I'll leave this as the main open question that we're going to tackle this year. So with that, let me end the talk here, and thank you for listening.
Okay, thank you very much. And so I think we have a bit of time for questions. So I think we have at least 2 hands raised, and so I'll let Baz go first.
Thank you for the very nice talk. Could you explain what you want to do with the front end? That was your previous slide.
Yes, let me go to that. So here. Yeah, I think so. I think this will depend on the particular project, but one could say here's a sort of, for instance, you want to formally verify some SNARK-based proof system. The backend part is the SNARK itself. So the SNARK takes in some error constraints, and then it does some stuff with the error constraints, and it produces a proof. The link here to the front end part is exactly which error constraints get put into the SNARK, right? Or the SNARK. And that is the link that I'm talking about.
So you go from SNARKs to the proof assistance, or the other way around? I mean, you have your blue arrow. It goes in 2 directions.
Yeah. Yes. So the 2 directions I meant more like the 2 parts can be integrated together, right? Like you may create, say, a third repo that imports ArkLib, imports Clean or other front-end projects, and then use both of them to formally specify like end-to-end a ZKVM, right? Both the front end, like how the different instructions are represented by circuits, but also the back end where how these constraints are actually proven, like from these constraints, how you actually generate proof for them.
And how do you want to connect ROC and ACL2 to Lean?
Oh, I think having a agreed upon constraint format would be the best way. I don't think it will be very easy. Well, SMT maybe we have Lean SMT, but basically ROC and ACL2, I'm not really sure. I think we will have some gaps there. Yeah.
There's one project we're working on together with, I mean, for the Ethereum Foundation that does cross compilation. I'll link it here between Lean and ROC.
Yeah.
And then I had a question about your next slide or a suggestion.
Of course.
Right. So about one, I think the first model you used for Oracle computation is close to FCF in ROC. And so for the categorical semantics, what we model in SSPRO is actually a monodal category or a tensor category. So that's sort of where you both have horizontal and vertical composition. So that may give some suggestion about the I mean where to look for the 2 squares if you want to have some motivation, but maybe have something else in mind.
No, I guess I was not aware of the 2 arrows. I'll look into it, but yeah, this is definitely in the range of what I'm looking for.
We formalized it, just haven't advertised it yet, but I'd be happy to tell you more at some point.
You can give a talk if you want.
Yeah. But thanks again for the very nice talk. Great work.
Thank you.
Okay, thank you. So yeah, maybe we'll have a talk from Baz or someone else involved as proof later on. And then I think question-wise, next up we have Divya.
Yeah, thank you again for the talk. I'm actually Baz already asked and answered the question, because I was already thinking there's a monoidal category probably involved in the semantics there. But well, they have already proved it, so that's nice. But also I was going to ask for lenses. Are you guys, do you have your own implementation of lenses? Because I don't think Lean has like a lens library like Haskell.
Yeah, Lean doesn't, and we basically roll ourselves based on polynomial functors. And I mean, the polynomial functors are just dependent lenses. So we just develop a theory of p functors extending what our mathlib has, and that's our current state.
Okay.
We haven't. I think it's on the roadmap that we will try to make specifying these lenses to be a lot more ergonomic, but so far we haven't made too much effort towards that.
Okay.
Okay, and then next up is James.
Hey, Quang.
Hey.
I think Boz mostly asked this already, but I guess what do you need from the front end for your picture near the end? Is it? I guess it sounds like mostly just like the constraints and the MLEs.
Yeah, so I guess this depends a lot on the particular like front end and back end you're talking about. So I'm not super sure. I think for Jolt, for instance, we do have these mix of constraints like ORNCS and the lookups and so on, that as long as we agree on a format that can represent all the constraints, then we can have a link between the two front end and back end. And ideally, I think this link should be established in a downstream repo that imports both of this and then make progress within that repo.
Okay. But we might want some coordination to make sure that they're interoperable and that kind of thing.
Yeah.
Okay, sounds good. Thanks.
Okay, thanks. And then next up is Derek.
Hey, Quang. Thanks for the talk. I had a question about mathlib and how useful you have found it in formalizing ArkLib, and whether, like, how much it is used, and whether you found any friction or difficulties kind of hooking it up, I guess, to some of the abstract concepts that you want in a more computational environment versus the more pure theoretical of mathlib.
Yes, thanks for the question. So my experience with mathlib is that I have contributed a fair number of PRs to mathlib in the process of developing ArkLib, and the PRs are received well. I think they are basically like very small PRs. I did not put any large things like trying to put computable polynomials into mathlib. So yeah, but I think reviewing in mathlib can be very slow. Maybe they'll get faster now that mathlib has more money. But there's, I think, always a sort of tension between what we want in ArkLib and the speed at which we want them versus the speed and the needs of mathlib. So for now, I am leaning more towards, if I want anything in ArkLib, I should just try to develop it myself, and then later on see if what people think.
Sure, if that makes sense. Cool, thanks.
Has anyone made a PR to CSLib yet? I think the review process there is maybe a bit nicer.
That's a good point. Yeah, we should look into it.
Yeah. So they were asking about upstreaming decoding theory into CSLib. When I complained that upstreaming it into MATLib would be too painful, they offered to put it in CSLib.
That would be nice. That would be really nice.
Yeah, we'll see. Once we finish the proofs, then we can do that. Okay, do we have any other final questions in the last 5 minutes we have from anyone else? And then, if not, then, well, first of all, thank you, Quang, for the fantastic talk. I guess there'll be maybe a shorter version of that at World Crypto in 2 months or so, maybe with some updates. And for anyone else, obviously, I heavily encourage coming to the talks, which are next week and the week after that. So next week, we'll focus on decoding theory in ArkLib, which I guess will also touch on maybe part of Derek's question about MATLib and how useful it's been to work with the way things are formalized in MATLib. And so Katie will be talking about this. And then the week after that, we'll have a talk by Julian from Nethermind about the Frey spec we now have in ArkLib as well, which is, I think, along with SumCheck, a nice milestone to have, obviously, like a specification for a SNARK that is actually, or part of a SNARK that is actually used in production. And so see you all in the next 2 weeks. And then there'll be more talks as well in February, but maybe more on the circuit side of things. And then maybe, hopefully, some future talk by Baz about maybe as proven the program logics there and categorical semantics and all of this. So yeah, thank you everyone for coming. I'll stop the recording and then we can leave it here for today.
Okay.
Thanks everyone.
Thanks, everyone.
Thank you.
Thank you.
Bye.
Thank you.
Thank you.